Good day, everyone. So, in this session, we'll discuss about different aspects of state space analysis. So, we'll discuss about state transition matrix. After that, we'll discuss about how to find out the transfer function from the state model equation, and then we'll from the transfer function how to convert the state space model, and then controllability and observability. So, these are things we are going to study in state space analysis. So state transition matrix is nothing but let's say a phi of S is a state transition matrix which is in S domain, so which is equal to Si minus A inverse. So inverse of Si minus A. So what is I? I is your identity matrix, that is 1 0 0 1. Okay, so it is a 2 by 2 matrix. And A, what is A here? So let's say your given state equation is like this. So x1 dot x2 dot, this is the matrix, and after this we have a matrix here 0 1 minus 2 minus 3 x1 x2 plus 0 1 y ut. So this matrix is your A matrix. So if you can find the inverse of this matrix, then that forms the state transition matrix. So inverse of any matrix, as you know, it's nothing but adjoint of that matrix divided by determinant of the matrix. Okay. So if you can do that one, then that gives rise to your state transition matrix. So your phi of S is equal to S inverse of Si minus A, and if you take its inverse Laplace transform, that is in time domain. Okay, so that is a state transition matrix. So Si minus A, so S, so identity matrix is 1 0 0 1 minus A is nothing but 0 1 minus 2 minus 3, and then we'll get uh, the we can find out the inverse of the matrix. So that is nothing but adjoint of Si minus A and determinant of Si minus A. A determinant of Si minus A is equal to nothing but here S square plus 3S plus 2. And adjoint of Si minus A is S plus 3, 1 minus 2S. Okay. So what is the inverse here then? Then adjoint divided by determinant. So S plus 3, 1 minus 2S. So it is divided by S square plus 3S plus 2. So we'll get, this is our inverse of the matrix Si minus A. So that is your state transition matrix in S domain. Now this S square plus 3S2 can be further converted into S plus 1 and S plus 2, because S square plus 3S plus 2 is a quadratic equation, and from that we can find out uh, the the state transition matrix in time domain is inverse of phi of S. So we'll get 2 into e to the power minus t minus e to the power minus 2t, e to the power minus t minus e to the minus 2t minus 2 e to the power minus t plus 2 into e to the power minus 2t minus e to the power minus t plus 2 into e to the minus 2. So this is a given state transition matrix in time domain. Okay. So just we take the inverse Laplace transform uh, of this S domain which is there. We have to take the inverse Laplace transform, and we get the state transition matrix in time domain. So this is about state transition matrix. The next we'll go to how to find out the transfer function if the state model is given. Okay. So now let's consider your x dot is equal to ax plus bu and y is equal to cx plus du. So this is your state model. So there are two equations that will be there. X dot, which is nothing but differentiation of x, ax plus bu, then y is equal to cx plus du. So what is your A matrix? 0 1 minus 2 minus 3. What is the B matrix? 0 1. And what is C matrix? 1 0. And here D is equal to 0. So after getting to know what is A, B, C and D matrix, we can find the transfer function like this. C Si minus A inverse plus B into D. So it's very simple. We have to take the inverse Laplace transform of Si minus A, just like we do find out the uh, inverse of any matrix. So to take the inverse of this matrix Si minus A, then multiply with C and B plus D, that gives rise to your transfer function. So S, so this is your identity matrix minus 0, minus 2, 1, minus 3. So your Si minus A is uh, S minus 1 to S plus 3. Okay. So then what is your adjoint of this matrix? So S plus 3 will go here, S will come here. Then you have to change the sign. So it will be minus 2 and 1. So this is your adjoint of this matrix. s plus 3 1 minus 2s, and what is the determinant of this matrix? It's s square plus 3s plus 2. Now what I say, so your transfer function will be c into si minus a inverse into b. Okay. Now all C matrix we know, A B matrix we know, Si minus A inverse just now we find out. So if we can multiply these three matrix, then we'll get this equation, this transfer function as 1 by s square plus 3s plus 2. Now we'll discuss about transfer function to state space equation in a state space analysis. Now let's consider the transfer function to states equation in a state space analysis. And let's consider the question is like this. A feedback system is having closed loop transfer function. Your CLTFS closed loop transfer function, which is equal to s square plus 3s plus 3 divided by s square plus 2s square plus 3s plus 1. Now construct the state model for this system. How to do? Now let's consider the transfer function, which we can divide into two parts. So this is y of ys divided by u of s. So we multiply x of s in the numerator and denominator. So 1 divided by s cube plus 2s square plus 3s plus 1. This is yours. And this is equation number A. So that will determine for state equation. And ys plus xfs, that is s square plus 3s plus 3. Let's consider this is your b equation, that is your output equation. Okay. Now first we'll see the state equation, then we'll go to output equation. Now for state equation, if you can see, so just we'll cross multiply the the here, so x of s with x square plus 2s square plus 3s plus 1. So if we can multiply here, we'll get the equation like this. And after that, we will take the inverse Laplace transform. So inverse Laplace transform, if we can take, then it will be y u of t is equal to x triple dot plus 2x double dot plus 3x dot plus x. Okay. Now here we have to take the approximation here. So x1 is equal to x. Let x1 is equal to x. So what will be here x2? X2 will be x dot. Okay. Now x dot will be x1 dot. Now let x3 is equal to x double dot. So x double dot will be x2 dot. So what is x3 dot? X3 dot will be x triple dot. Okay. So this is the approximation we take, and this approximation which we take, we have to put it here. Then we'll get this equation. Then we'll bring x3 dot to this side and bring all this to other side. So x3 dot will be minus x1 minus 3x2 minus 2x3 plus ut. Now the standard form of making the state equation is x dot is equal to ax plus bu. So this is x3 dot, x2 dot is here and x1 dot is here. So this makes the state equation. And if you can put it in a matrix form, so it will come like this: x1 dot, x2 dot, x3 dot, 0 1 0 0 0 1 minus 1 minus 3 minus 2 x1 x2 x3 plus 0 0 1 u of t. So this is your state equation. Now how to find out the output equation? So let's consider y of s is equal to s square plus xs plus 3s x into 3 into x of s. What we have to do? This in this cases we have to cross multiply here. So y of s is equal to x of s into s square plus 3s plus 3. So that we are doing here. So then again we have to take the inverse Laplace transform. So we'll get y t is equal to x double dot plus 3x dot plus 3x. Now the approximation which we took it here, we have to put all this approximation here. Then we'll get y t is equal to 3x1 plus 3x2 plus x3. Okay. Now this is your output equation. So we have to make sure that our output equation is in the form of y is equal to cx plus du. So this is a c and this is a d. This is your output equation. Then how to find out the controllability and observability of the control system, that we're going to do in this uh, example. Now let's consider a transfer function which is given by y of s is equal to u of s, which is equal to 2 divided by s cube plus 6s square plus 11s plus 6. Okay. So how to find out the controllability? So let's QC is your let's say to find out controllability, C for controllability. So it is given by this matrix B, A, B, A square B, like this, A to the power n minus 1 B. And what is observability? Let's say O means observability QO. So it's C transpose, A transpose, C transpose, A transpose square, C transpose, A transpose to the power n minus 1 C transpose. So this is your to find out controllability and observability. Now we have to do the same thing that we did in the last example. So we have to cross multiply this transfer function, and so if you can cross multiply, so it will be y triple dot t 6 y double dot t plus 11 y dot t plus 6 y t is equal to 2 ut. Okay. Now here you have to take the approximation. Let's x1 is equal to yt. So x2 will be x1 dot. So that is nothing but y dot t, and x3 is equal to x2 dot, that is y double dot t, and x4 is equal to x3 dot equal y triple dot t. So one dot means the single differentiation, double dot means two second differentiation, and triple dot means so it is uh, second third order differentiation. Okay, so like this. So single differentiations, double differentiation, and triple differentiation like this. So your y triple dot t will be 2 ut minus 6 y double dot t minus 11 y dot t minus 6 yt. So this y triple dot t nothing but your x3 dot. So the approximation which we take here, just we put it here, and then we form the we can find out the matrix here. So this is our A matrix here, 0 1 0 0 0 1 minus 6 minus 11 minus 6. This is B matrix 0 0 2. C matrix is 1 0 0. Okay. So this is A B C. After getting, then you have to put this value B A B A square B like this. So that gives rise to your so this is your AB. This is A square B. B you already know. Now if you can find out, so it will come like so. So your QC will be 0 0 2 0 2 minus 12 2 minus 12 50. So after that we have to take the its magnitude. So for controllability test, if the modulus or the magnitude is a non-zero value, that means it's not equal to 0, then it is a controllable. So remember that if you want to find out whether it is controllable or not, so the matrix has to be non-singular matrix. That means it should not be equal to 0, and the rank will be equal to that. Let's say 3 by 3 matrix, so rank should be 3. If this condition satisfies, then it is a controllable. Similarly, for observability test, so here we have to take C transpose, A transpose, C transpose, A transpose, C transpose. So after getting the transpose of any matrix, which we have to change row into column like this. And if you can see here, we get the matrix QO, that is Q matrix 1 0 0 0 1 0 0 0 1. So for observability also, the matrix has to be non-singular matrix, that means not equal to 0. In this cases, if we take the modulus, then it is 1, which is not equal to 0, and it is rank is equal to 3. So it is observable. Okay. So this way we can determine whether the given transfer function is controllable or observable or not. Okay. So hope you all of you can understand this thing. Thank you everyone.